Good afternoon, professors and students. It's a pleasure to have you with us in today's presentation. The topic of the presentation today is effect of orange juice on the surface roughness of polished translucent zirconia. In modern dentistry, there are many options for restoration of teeth regarding material, especially dental crowns, which require multiple aspects of physical property in order to imitate natural dental tissue as much as possible. A prime candidate currently is zirconia, a very durable, highly aesthetic, and very highly adjustable in color to adapt to patient's dental shape. Zirconia crowns made from the lab are all glazed, but during trying step in clinic, minimal adjustment is a common procedure which removes the glaze layer for better seating. However, adjust crown is not returned to lab for glazing. To compensate, polishing after adjustment is necessary for aesthetic and longevity by reducing surface roughness. Usage of crown will also deteriorate the glaze layer, increasing its surface roughness, thus leading to our question on the intensity of the effect upon surface roughness of zirconia crown, modified by types and temperature of ring. Objective of our research. First is to find out the degree of surface roughness of zirconia altered by different types of beverage. Second is to find out the degree of surface roughness of zirconia altered by different temperatures of beverage. Review literature. Dental ceramic can be divided into three types: glass matrix ceramic, polycrystalline ceramic, and resin matrix ceramic. All of them has different properties, and its usage depends on patient needs and suitability. Glass matrix ceramic has matrix and glass face. Polycrystalline ceramic has crystalline face but no glass face. Resin matrix ceramic has porcelain ceramic crystal embedded within resin matrix. The one that we are focusing on is dental zirconia, which is a polycrystalline ceramic. Due to its natural behavior, zirconia can undergo through different phases depending on the temperature it is heated to. To prevent its dynamic behavior, a stabilizer element, yttrium, is used to stabilize the phase zirconia is in. The most common amount is 5% mole of yttrium, thus name is 5-YTZP. Zirconia phase transformation or allotropy is a series to molecular transformation of zirconia due to the change in temperature. When zirconia is heated up to a certain temperature, its molecular structure changes. For example, monoclinic phase. A general zirconia phase exists in room temperature to 1170 Celsius. When heated to above 1170 Celsius, it changes to the tetragonal phase. And the desired phase for dental use is the tetragonal phase due to its higher strength and maintain the ability of allotropy. Zirconia transformation toughening. Tetragonal phase zirconia can transform into monoclinic phase at high stress area, which is a crack area. Monoclinic phase has higher volume than tetragonal phase, allowing to stop propagation of the crack. Then surface modification. Polishing of zirconia is usually done with rotary instrument with diamond grain abrasive, which is often done chairside. It is recommended to sequentially polish zirconia in order from coarse grain 150 micrometers to fine grain 7.5 micrometers with water coolant. Changes in surface roughness of zirconia can be altered by mechanical environment factors such as parafunctional habits and masticatori stress. The chemical environment factors such as low temperature degradation and pH. Surface roughness can be measured using a machine called profilometer, which can be divided into two types. First, one contact profilometer, which uses stylus to run through the surface, and second, non-contact profilometer, which uses reflection of the light to record irregularity. Surface roughness parameters. RA, the arithmetic average height parameter. It is an arithmetical mean of absolute value of the profile deviation from the mean line of the roughness profile. It is most universally used surface roughness parameter for general quality control because the instruments are simple to measure and the parameter is easy to define. It does not give any wavelength information and is not sensitive to small change in profile. Materials and methods. Materials for our research: beverage, distilled water, as a control group and orange juice as an experimental group. 5 YTZP Zirconia, dental putty, pomade polishing kits. Other materials are as seen. Beverage types and storage. Beverage samples are divided into subsets in accordance to temperature and to liquid. The container will be the petri dish, in which one subset will be in each petri dish containing 9 ml of the sample beverage. The samples are cleaned in ultrasonic cleaner, again in the same setting. For measurement, non-contact profilometer was chosen to measure surface roughness of all samples containing our area to adjust 3 by 3 millimeters as to represent the whole. To ensure the same location of measurement, a jig made from dental putty with size of 5 by 5 millimeters is placed over the Zirconia sample as a guide. And 3 points within the jig are chosen which are center, lower left, and level and upper right with at least 1 millimeter away from jig. And this is an illustration of our working sequence after emission to non-contact profilometer. Zirconia samples will be immersed in beverage within petri dish for 168 hours or 7 days, with each petri dish representing 4 subsets of our temperature and types of beverage. Beverages are refreshed every 12 hours to maintain the environment of Zirconia is in. pH measure was also used to help confirm the beverage pH level. After immersion, the samples are then cleaned again in ultrasonic cleaner to remove anything potential debris or contaminant from the beverage that might appear under non-contact profilometer. The samples are then heated in hot air oven before another round under profilometer. The exact same jig will be used to guide to replicate the same position samples are initially measured. The picture shown is an example for reading of non-contact profilometer. Example of 3 lines on the non-contact profilometer image for RA. And the Levine test showed the variance between groups are not statistically different, thus two-way ANOVA was performed. The results show that types of beverage and temperature did not significantly affect to surface roughness of polished translucent zirconia, and both factors together did not produce any significant effect. Thus, the first null hypothesis was accepted due to there is no significant difference of RA when immersion in distilled water and orange juice, with the control group being distilled water immersion. And the second null hypothesis was also accepted due to there is no significance of RA among immersion in beverage at cold temperature of 5 Celsius and room temperature of 25 Celsius. Discussion: the surface of zirconia restoration is usually exposed to changing oral environment and can be degraded from food ingredient or beverage with acidic agents, resulting in changing of RA of polished translucent zirconia. The result of this research indicated that low pH beverage had no effect on surface roughness of translucent monolithic zirconia. Citric acid weakly degraded ceramic material by chilling and ion leaching mechanism, which are roughening the surface in 8 ounces of immersion. Citric acid from the acidic beverage was shown to increase the surface roughness of feldspathic, aluminous, leucite reinforced, and fluoroapatite ceramic after 160 and 8 ounces of immersion. In contrast to C et al., the study of 20% of citric acid could not damage the translucent zirconia surface in the ambient temperature for 7 and 14 days, which was the same as the observed in the study of C et al. The exchange in surface roughness could be due to the surface texture being exposed to various types and temperature of exposure solution. Orange juice is one of the most commonly consumed beverages around the world these days. This contains some acidic agents which can cause dental erosion, mainly citric acid and ascorbic acid. It is known that restorative material can absorb water and other acidic fluids, causing surface degradation, and the previous study have shown that water could act as a conductor for acidic penetration. The two temperatures chosen for this research were 5 Celsius, which is the temperature of ice beverage, and 25 Celsius for room temperature beverage. The 5 Celsius was recorded within the ice beverage as it is melting and absorb heat from surroundings, and the temperature of 25 Celsius was recorded within an air-conditioned room. The temperature of 37 Celsius was not chosen because the drink that will be in contact with zirconia will mostly be at 25 Celsius at a standard room temperature rather than body temperatures. The drink chosen are typically swallowed within a few seconds, not left until the temperature has adjusted to body temperature. And the main reason for this regarding hot temperature was because orange juice was not typically drunk hot. High temperature was entirely disregarded as it does not represent real-life practice. The further investigation can be conducted at higher temperature and other beverage, such as coffee, which could be served in hot and cold for exploring the other end of spectrum to see if high temperature could produce significant results or not, despite choosing drink not typically served hot. Instead of using artificial saliva as our control group, distilled water was chosen to isolate our variable from other unnecessary factors such as protein and enzymes. This was done to prevent any possible intervention and contamination that might affect the pH value of entire solution. Distilled water was preferred as its pH is neutral and purified from contaminants. The choosing duration for immersion was 160 and 68 hours to represent real-life scenario exposure of beverage for 22 years. Our research conclusion from the limitation of current study, it could be conclude as following. The surface roughness of polished 5-white TZP was not affected by orange juice, and the increased temperature of orange juice from 5 Celsius to 25 Celsius did not affect the surface roughness of 5-white TZP. Thus, in terms of the surface roughness changing, the 5-white TZP was not affected by orange juice at cold and room temperature when comparing to distilled water. Okay, thank you for listening patiently and attentively. And thank you our advisors, Ajahn Thaksit, Jarat Sang Phaisan, and Ajahn Wasan Wattanasak. Thank you.
Thank you very much, Dr. Nattida, for the presentation. Is there any question from the audience? Okay, if there is no the question from the audience, so I have some question to ask, and why do you choose 168 hours for immerse in the orange juice?
Okay.
Any research that suggests this amount of time?
According to our scientific journal, 165 hours is the minimum time for acidic drink to produce any effect on sample surface.
Of which kind of material? I think it's not translucent zirconia, right? I mean, on
the lithium, about the lithium disilicate.
Okay. Because in my opinion, I think that it is too short time to give the effects zirconia, because zirconia is very inert material, and it's like if you review about the etching of zirconia, like that they're subject to autoclave or thermocycling, it will take a long time, like that represent like a year or 10 years. It costs very little change on the surface of the zirconia. And so, I mean, only emerged in the hot, in the orange juice. I think it's too short time. And so that's why you didn't see the result that is different. I mean, my question is like, is there any other research about zirconia and the effect of the beverage surface roughness? You have, or your research is the first research about this? Do you have information about this? Because
Yes.
I read the discussion. I mean, you have a discussion, and it seemed to be that the orange juice or other beverage can cause the effect on the surface roughness of other material, right?
Yes.
But I mean, do you write down about the zirconia in the paper?
Paper.
I mean, in your discussion.
Yes, there is a paper from the Thai master degree students write about like a monolithic zirconia or something, and she did with low pH beverage and used like a contact profilometer to evaluate the surface roughness.
And what is the result? Are there any different?
There is difference, but no significant difference. Like statistically, it's not accept P is more than 0.05. So it's different, but no significant difference. Yeah.
Okay. And maybe in your
Research.
The point of your research may be that you polish before, right? Maybe it's different from them. And this is the point that you would like to see, like if you polish it before, it's not direct from the furnace or manufacturer, maybe it can cause the surface roughness. Subject to the orange, right? To the orange.
Yes, that's right.
Your point, I think. That's why you would like to do this research.
Because in the real life in the clinic, we polish the zirconia before. Maybe we have to polish it further than the manufacturer from the company, because if we insert in the mouth and it's not cannot be seen, we have to polish it, and then there may be some low temperature decondition or something on it before insert. And this is the point why we choose a polished translucent zirconia for this research.
Okay, the time is up already.
Okay.
Please move to the next presenter. Thank you, Dr. Nattida, for the presentation.